and pages. Sorry, talking about anatomy and physiology of memorizing. Okay, thanks. Always first hour. Got a little jab to say stuff. Always got the little things. Gets my day started. All right, but anyway, irregardless, all right, there will be some memorization first hour. All right, there will be memorization, so we will have that. So, with that being said, here's the next set of identities. Okay, so we're going to go ahead and do this again. Today is here are the identities. Let's use them as properties. And then on Monday, we're going to use these identities to help solve. All right. So that's how these days have gone this past week. Identities, use them. Next day, solve with them. And then, blah, 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 blah. So here are the identities for some. And I'm just going to go ahead and go through my process, how I have these memorized. So for sign, some identity, the signs are the same. So let's put a plus right in there. All right. So for some and difference identities for sign, the signs are the same. So I'm going to go ahead and put a minus here. All right. Sum of a difference of two angle measures. Well, then therefore there's a difference there. And then this is how sign works. And get used to your form or your letters here. That is alpha. So sine alpha plus beta is sine alpha cosine beta. Okay, so it's sine cosine, and you alternate the angle measures. It's a really easy memorization structure. Then the next one is plus sine. Well, I did sine alpha here, so now this is sine beta. And I did cosine beta here, so this is cosine alpha. All right, so it's just sine. Sines are the same. Sine cosine, sine cosine, and switch the angle measures. Really not a tough memorization, because then the next one is exactly the same structure, except sines are the same. So you can expect some sort of having to choose which one does this match up with, sort of like memorization scenario. Okay. And then we're going to use it. So this is just a definition. We're not going to derive where it comes from. It just does exist, and it's used a lot in trigonometric simplifications and so on and so on and so forth. For cosine, it has a distinct different structure. Number one, for cosine, the signs are different. So sum is a difference. Okay. So that's why I go back to for the sine formulas, sine, SIGN, is the same. All right, trying to help you memorize little tricks. And then cosine is a very distinct structure that is different than the other one. Cosine is cosine, cosine, sine, sine. And again, this is just here it is. These are the identities that are true. We're not going to derive them, we are going to memorize them. All right, and then cosines, the signs are different, and it's the same exact structure. All right, and then we're going to actually use them and see how we fill in parts and do this and do that. How do we manipulate them? All right, AP, big idea, always like alternative forms of the same thing, using formulas or whatever. And that's all they really do. I'm going to be honest with you. Your responsibility on these identities is about 25% of what students had to do last year. It really is, because solving identities can get really, really complicated. I think I was saying during the quizzes yesterday, this is barely like a level 2.5, 3 question. And at first I said out of 5, but I go literally probably out of 10. Identities could be like 6, 7, 8 steps. How many people did a geometric proof ever before? Geometry proofs? Anybody? Okay, nobody raised their hand. Somebody did there. Well, they're like that, and they can be like that. So just rejoice a little bit that it's not as bad as it used to be. At least your responsibility. All right, this is just a manipulation of the formula. Okay, so it's sine sum formula. So what I have to do is put the parts in. I'm just going to be a lecturer here and just show you how this works out. Well, the sine sum formula is this. Let's rewrite it here. Sine of alpha plus beta. Because again, a lot of times students that I've seen in the past don't work with formulas well. They don't know how they work, how they function, and how we replace things. Sine formula, the sine is the same. So again, in doing this too, I'm trying to have you memorize. And then it's sine, cosine, sine, wait, I need something different. Sine, cosine. Okay, you flip the angle measures on the second part of this. So who's taking the place of alpha? Again, as being trying to be the best teacher I possibly can, all you do is replace alpha and beta with those two angle measures. And then lo and behold, here we go. Sine of pi over 4. I told you, the unit circle is not going away. Told you that before break. If we're not memorizing this, we are doomed. And everything else will crumble if we can't get these memorized. Okay, what's sine and cosine of pi over 4? 3, 2, 1, go. Root 2 over 2. Anyone that puts the word sine next to that root 2 over 2, you still don't know the simple concept that you sine an angle measure, you get a ratio. So anytime anyone puts the word sine in front of this root 2 over 2, I got to mark them wrong. All right? Just being honest. All right, and then over here, we're going to put that root 2 over 2 because they're both in quadrant 1, so they're both positive. So be careful on that. All right, and then what's sine of an over 3? Well, sine of an over 6 is 1/2. So what's sine of an over 3? 3, 2, 1, go. Root 3 over 2. So what does that mean? Cosine of an over... Oh, I made a mistake. Where is 5 pi over 3? Where's that located? Where's 5 pi over 3? What quadrant? 4. This is 6 pi over 3. I still had someone say 3. This is 6 pi over 3, so that's where 5 pi over 3 is. So what's sine in quadrant 4, positive or negative? The answer is negative. Then what's cosine of an over 3? By the way, if you had to go into level 1 of trig here, an over 3 is a 60. This is what I had my students do last year. Oh, that's root 3. This is 1. This is 2. And that's negative. And then they can play Sir Kicks or Ticks or SOHCAHTOA. We got to do something, though, to get these ratios figured out. So what's the cosine of 5 pi over 3? 1/2. Right? And these are not the things that should be killing us right now. But if they are, that is your situation. Root 2 over 4. And then this is negative. Root 3 times root 2 is root 6 over 4. Often you see this written as one denominator. And I'm going to cowboy this and get this out of the way of the one over here. Okay? And that's it. It's writing the answer in exact form. Engineers need stuff in exact form so things fit perfectly. So that's a big component of this, different ways of getting exact answers kind of idea. All right, just for lecture purposes, we're going to keep going. And then memorization. So this is like this formula, subtract. The cosine formulas are cosine, cosine, sine, sine. Okay, very simple thing to separate, memorize, so on and so forth. And then what's the sign? Is it plus or minus? 3, 2, 1, go. Plus. Okay, it's opposite. All right, so cosine signs are opposite. All right, and then what's taking the place of alpha? 7 pi over 4. Right, and I shouldn't have to draw, but if you do have to draw, get it in a quadrant, get those angle measures, go for it. What quadrant is 7 pi over 4? What quadrant is that? 4. So we know our signs. So this is positive root 2 over 2 because cosine in quadrant 2 or 3, quadrant 4, sorry, is positive. And then this one's negative root 2 over 2. Again, not covering where we get those from. Over 4s are easy. Tangent of over 4s are 1. So that's all that happens there. And then yet again, we have an over 3. So we already had these ratios. But 2 pi over 3 is in quadrant 2, ASTC. Again, things to write at the top of your page. If you're level 0 in trig, Sir Kicks or Ticks, so you remember the letters, or even SOHCAHTOA is okay, I guess. And then quadrant 2, sine is positive, and it's sine of an over 3 yet again is root 3 over 2. Same ratios from the last one. And yes, when you exercise these rules and deal with our common ratios or common trig values of over 3s, over 6s, over 4s, the answers end up being pretty similar. All right, you get a root 2, you get a root 6, you get a 4. This happens a lot. It's because we're in the little beginning stages of doing the sum rule, just to practice it a little bit with ratios that you know. Certainly an engineer gets more complicated with it. All right. So it's really kind of like a wax on, wax off. Just here's, some ratios that you know. Practice the sum formula with ratios you know. All right. Just being honest, it's the truth. Fumble. All right. Simplify. Lisa's got a coffee all over the floor. Simplify sine of x minus pi over 6. Sine of x, cosine of pi over 6. What do I put here? Minus or plus? Minus. And then it's sine of pi over 6, cosine of x. This is weird. One of the angles is unknown, so it'll remain unknown. But I do know the sine. Oh my gosh. I've asked this a billion times. What is the sine of pi over 6, which starts everything? 3, 2, 1, go. 1/2. Still not getting that answer. All right, and then what's the cosine of pi over 6 then? What does that become? We're 3 over 2, and we want to write that first. That's the commutative property. I can switch these two, cosine of pi over 6 first. Then quite honestly, these can't be combined because that's like x and this is like y. These are different variables. So guess what? That's simplified. Great. Fantastic. Next one might be a little bit better. And things like this creates new identities sometimes using, and that's going to happen actually on our next page. Okay, so this one is, okay, what's cosine? Cosine is cosine, cosine. And then what's the sign here? Plus or minus? 3, 2, 1, go. This is why you do this. This is why you do your homework. Wax on, say it. Okay, you do your homework because then you sit there and think you don't have it in front of you. You try to write it down and then check. This is why I said since August why you don't copy keys. Here he goes again. Blah, blah, blah. All right. But anyway, when you're doing this stuff gets solidified, and that's why it's okay to ask you a very, 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 very simple formula quiz. Very simple. Very, 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 very. Okay, now what's the cosine of pi over 2? Well, this is what you want to do here. Yoink, yoink. Here's pi over 2. What is that coordinate? What is that coordinate? 0, 1. So what's the cosine of pi over 2? 0. This one does simplify. This is what I mean about sometimes when you use the sum or difference rule, they come up with new identities that are popular and used. All right, and you'll see this in a minute. What's the sine of pi over 2? 1. But we got that minus. Ooh. Okay, so this is nothing. So this turns into negative sine of x. Weird. So we could actually call that like a newer identity that's simplified and small, but you don't have to have that memorized. You just have to, we'd ask you a question like that just to exercise it. And then yet again, you're doing evaluations without a calculator from the unit circle. So it's all good. All right, now you want to get nuts? Let's get nuts. So Fattermact, I'm going to do this. I couldn't, anyone? Care less that this may confuse you, but it shouldn't. Do you know what pi over 4 plus 5 pi over 3 is? Don't say 6 pi over 7. Get out. All right? Get out. Get out. Get out. All right. So what do you need? A common denominator. What is the common denominator between 4 and 3? 12. So this could be rewritten as 3 pi over 12, right? Plus, and then what does this become? What does that become? Okay, so that becomes 20 pi over 12. So this is actually equivalent to finding the sine of 23 pi over 12. That's what we just did. That's what we just did in this one. Because now I'm going to ask you this question, and you got to come up with a sum that actually equals 23 pi over 12, and then do the trigonometry. So now it's just one little extra step. And I could have done the same with this. Same thing. The common denominator is 12 on this one. So 3 to 21 minus 8. What's 21 minus 8? What's 21 minus 8? What's 21 minus 8? Anyone? 21 minus 8? 13 pi over 12. This is actually what we just did on this one. We literally found the exact answer of cosine of 13 pi over 12. All I did was subtract those two, getting a common denominator. Okay, so that's why, again, wax on, say it. We're doing just like basic things. You're going to see a lot of over 12s because over 12s are really nice. Like what's 5 pi over 12? 3 pi over 12 plus what? What's left over, everybody? 2 pi over 12. But you know what this becomes then? This is pi over 4. Hey, that's a familiar one. And then this is pi over 6. Hey, that's a familiar one. That's why we can't get too crazy about the denominator. We're at level 1 of just introducing the sum rule. It's got to be angles from our unit circle for us to be able to work with it. I don't know if I have any others. Yeah, I think that's about it, unless I'm struggling to think here. I could do this. You want to get nuts? Let's get nuts. Uh, how about this one? No, that wouldn't work. Eight. I'm trying to. Oh, I'm excited. Wait, am I? Yes. Wait, hold on. Okay, yes. How about this one? 8 pi over 12. Wait a minute. That's larger. That's larger. Okay, what would I have to do to get to 5 pi over 12? What operation would I have to use? Subtraction. And then what would I have left? What would be the subtraction? What would I have to subtract to get this to equal that? 3 pi over 12. So why did that work? Because 8 pi over 12 is, I'm nervous. 2, 4, 4, 8, 4 goes into both of them. So that's 2 pi over 3 minus 3 goes into 12 4 times. Aren't those unit circle values? Yes, right? So I can pick a sum or a difference to equal the angle measure that I have and then use that as a formula thing. Got it? So I can do either or. I used to like doing, hey, let's do both. All right. And then see how they end up being the same answer. But, the students don't care much about that. So we'll just leave it at that. All right. So sine 5 pi over 12, I could pick one or the other. All right. So I'm going to do that one. I'm going to do the red one, even though this is green. I'll do the first one. So sine of 3 pi over 12 plus 2 pi over 12. And you got to make sure that these end up reducing to be on your unit circle. All right. You can't do 1 pi over 12 plus 4 pi over 12. Pi over 12 isn't on your unit circle. 4 pi over 12 is, but 1 pi over 12 is. 1 plus 4 is 5. The sum works, but it doesn't end up being on your unit circle. And that's going to be more of the same. Again, when you do these things, you get the same answers. Like they keep showing up. Right, so this equals sine cosine. That's what the sine rule is. Again, valid homework doing. Practice happens. And then for sine, sines are the same. And then it's sine switch, cosine switch. It's a very simple memorization. No problems. What's the sine of pi over 4? Yet again, this is why this is the argument. How people still don't know this when you've had to write sine of pi over 4 equals root 2 over 2 so many times. All right, and then so many times I've told you sine of over 6s is a half, so cosine of over 6s is that other ratio. And again, why am I putting them all as positive? Because you're all in quadrant 1. So same old, same old. This is root 6 This is root 2 all over the common 4. Common denominators there. So again, that's another thing about really identifying a charlatan or not. When you do these things, look at, we got root 6, root 2, and 4. Take a guess what kind of answers might happen on our test next week. It's going to be a root 6, a root 2, and a 4. All right. And we get people that just have no semblance of a correct answer on those. It's a little troubling sometimes, a little troubling. So let's do better. All right, and then there's the double angle formulas. I will actually derive this. You know what? Did you know that 3 plus 3 is equal to 2 times 3? Anyone? Right? Right. That's what multiplication is. It's a form of addition. So 2 theta, sorry, wrong, 2 alpha does equal alpha plus alpha. Am I right or am I wrong? First hour, someone just went like this? I don't know. It's true. Okay, so, all right, so that's what I'm going to do first. Sine alpha plus alpha. Anyone have troubles writing alpha? Isn't that kind of a hard variable to write? Yes? Yes, Mr. Samuelis. Okay, now watch this. This becomes, well, wait a minute. These are the same angle measures. So sine alpha, how does sine work? It's sine cosine. But wait, it's the same angle measure because they're the same angle in both positions. And then what do we do for sine? We add, and then we switch. But is there any change? No, because the variables are the same for both. The angles are equal. And lo and behold, look at what we have. We have a sine cosine, same angle measures. We have another sine cosine of the same angle measures. Those added together are how many of those? Just like alpha plus alpha is 2 alpha, this is 2 of these sine alphas, cosine alphas. So that is the identity for sine double angles. And we derived it from our sum formula. Okay? Lecture. Really not much more you can do with identities. Just going to shove them in the face and use them and memorize them. All right, and then cosine. All right, this one's a little weirder. Okay, so what do we do for cosine alpha or 2 alpha? We do that. And then how does cosine work? It's cosine. So it's cosine. Cosine alpha. Weird. Sorry, my alphas are getting a little weird. What's cosine alpha times cosine alpha? What is that? They're the same angle measure. So that's cosine squared. You got it. And then what do we do for cosine? Plus becomes what? Minus. And then what's sine alpha? Sine. Oh my gosh, my alphas are getting destroyed here. All right, sine squared of alpha. This is why you're not going to like cosine 2 theta rules, because there are 3 different possibilities. So let's highlight this one in yellow. Why? It's because of the Pythagorean theorem. Here's what I can do, and I'm going to do the work off to the side. You could do one of 2 things. You could replace this sine squared with what it's equal to in terms of cosine squared because of the Pythagorean identities. So what is that? Remember, sine squared plus cosine squared equals 1, and I subtract them. So what's sine squared equal to? 1 minus cos. It's drink time. Mr. Samuelis has asked me to answer a question. I refuse to do it. Glug. Okay, so distribute that negative, fumble, and then that is 2 cosine squareds. 2 cosine squareds minus 1. Okay, so follow the negative there. See that? So -1, and then this becomes a positive cosine squared with another positive cosine squared. So cosine 2 theta, the only reason it has three different properties is because of a manipulation with a Pythagorean identity. Or I could change this to 1 minus sine squared of alpha, and then minus another sine squared. So go back to the original yellow. And I guess I will highlight this in yellow. I took the yellow and I did two different manipulations with it. I did two different changes, and I'll highlight that with the parentheses there. So I changed that cosine squared now to 1 minus sine squared because that's what it is equal to in the Pythagorean identity sense. And then that creates a second unique rule for the cosine 2 theta rule. So sometimes it's nicer to use one depending on what's given. I like using the second two because you have one variable. It's either cosine or sine, but you have options. Okay, so here we go. Equivalent forms. They love it. They love it. All right, they love it. So first of all, cosine 2 theta rules. When I look at my multiple choice, some fall out right away. My cosine 2 theta rules has squareds in it. All right, look at the formula. So you're gone. This is trying to be like a sign trick. All right, this one's out. Process of elimination. All right, and then when I look at my other ones, the only thing I can think of is this. I do have one where I have sine all by itself, so a sine squared, and I have another one that has a cosine squared by itself. This one's off because what's supposed to be right here? Look at the formula up there. What's supposed to be right there? No, look at what I just circled. What's supposed to be right there for my sine rule? Minus. All right. So I could try this. I could say, okay, 4 and then cosine 2 theta. One possibility is replacing that with 1 minus sine squared. I said theta, and that's x. If I distribute that, the thing that's off is the minus sign, right? So this is out. All right. And then the only other manipulation I could do is replacing this and see which one's right here. I know which one it is. Actually, yeah, okay, good. Thank goodness. That is the other change to cosine squared. We'll say x minus 1. And then when I distribute this, that comes out. Okay. So equivalent forms, it's just a tricky question. Can you match which one this is emulating? All right, this is taking a little while, but really as I go through the notes, these really shouldn't be bad as we filter through if we're focusing and paying attention here. We love these. We used to ask these all the time. This is a perfect multiple choice question. So give me the equivalent form of this. Well, which rule is this when it's cosine, cosine, sine, sine? Is that a cosine rule or a sine rule? That's a cosine rule. And then which one is it? Is it a sum rule or is it a difference rule? That's a sum. Okay, that's it. That's the purpose of this. Manipulating the formula, recognition. Recognition is all it is. And then who ends up being alpha and beta? I'm out of highlighters here. It's just those two angle measures. Look at that. 5 pi over 9 and 3 pi over 9. What's 5 plus 3? Someone over there went like this again. Same person. I was talking about over there. 8 pi over 9, and it's the sum rule. So boom shakalaka. All right? Everyone okay over there? What happened? Someone shove your fumble? Okay. All right. How's everyone level right now? Go like this, or pick a different. No, I'm just kidding. Second hour, I thought I flipped them off yesterday. All I did, I was teaching, and I went like this, and I was pointing. And then, third hour. Anthony M. He goes, I'm sorry that you had to flip us off today. I go, what are you talking about? Then I thought he started rumors. And did anyone hear that rumor? I flipped off third hour. Okay, good. Thank God. Because I didn't. It was a lie. That's part of like social media. Just because a million people follow it doesn't make it true. Anyway, another lesson for the kids. Okay. What kind of trig have we been doing since February 1st? Coordinates. So this is a coordinate plane. So do you remember this? No, he never teaches anything. Remember drawing a triangle? You remember? Okay, and then if this is the coordinate, it's -2 here. It's root 5 here. And then how could I get r? What would I have to do? I would have to use the Pythagorean theorem. But it's a waste of time. Look at your picture. What is r? It's already on the page. I like saying 1 though, because what kind of circle have we been dealing with? The unit, but it's saying that it's 3 because I see that point right there. But I like it. Okay, unit circle is 1, but it's not. You have to look at the picture. Okay, so don't you agree that you could find, this is alpha, that you could find the sine of alpha real easy? The sine of alpha is, well, sorry, I almost made a mistake. Not easy for me. It's root 5 over 3. I almost did -2 over 3 because -2 over 3 is cosine. All right, going slow, just trying to get the students, let it sponge in their head. And then there is tangent rules. But do we have any tan rules up there? Yes or no? I wonder if they're going to ignore that. That'd be another reason why you're even like 20% of what students had to do last year, because there's a sum and difference rule for tan. And I don't know if we're actually doing that. I probably should know. But anyway. Oh, and then I have to go over here. All right, here's beta. Here's beta. Remember this? Okay. 3 comma root 7. And then what's this radius? 4. Okay. You know what? I can prove it. 3 squared is 9. Root 7 squared is 7. 9 plus 7 is 16. The square root of 16 is 4. Okay. So it's all proven. So the sine of beta is equal to root 7 over 4. By the way, you could tell that these are not unit circle evaluations. Doesn't always have to be. And then 3/4. Okay, well, now we're really set up for all of these. We're set up for all of them. For cosine 2 alpha, you need to, and that does have to be one of them, but you have to pick one. You have to pick one. So this is why I always say just pick one that has just one of them. So which one do you want, sine or cosine? Tell me. Nobody's saying a word. I heard a sine. So that means I have to use the 1 minus 2 sine squared of alpha. You have 3 choices. Okay, that's what you have on this. 3 choices. So somebody said pick the sine one. Do I have the sine one right? I have people making faces over there, right? See that one? 1 minus 2 sine squared of alpha. And then notice the arguments changed. The arguments changed. Now it's not double this angle measure. It's just the angle measure that I see here. By the way, though, do you know where this might be? What's 2 times 180? What's 2 times 180? 360. What's 2 times 90? 180. So this, wherever this angle measure is, double that is either in quadrant 3 or quadrant 4. It's one or the other. All right, I just want you to know what you're doing. You're actually now finding the double this angle measure. What is the trig of it? What is the cosine of it? All right. So I don't know what quadrant it's in, though. I can maybe assess it after I get my answer, though. So what is the sine of alpha? Root 5 over 3. So here's what happens. You replace sine of alpha with root 5 over 3 and then square it. Remember I told you that's what it means to sine squared? You evaluate the sine, then you square the answer. Got it? Okay, so now this is 1 minus 2 times root 5 squared is 5. 3 squared is 9. Okay, I know what quadrant this is in. 1 minus. Now again, these fractions. I'm just going to tell you. You just multiply the 5 by 2, not both. All right, so 2 times 5 is 10. 10 ninths. You know what 1 minus 10 ninths is? Negative anyone? Negative anyone? Negative. Okay, this is 9 ninths. So negative 1 ninth. Okay, so I crossed off the 1 and made it 9 ninths. So you know where 2 alpha is? What's cosine in quadrant 4? What's cosine in quadrant 4? Positive or negative? Positive. What's cosine in quadrant 3? Negative. Do you know where 2 alpha is actually in? It's in actually quadrant 3 because you got a negative cosine value. This is higher level thinking now, but it's not really that big. All right. So the double of this angle measure, this was probably more like over here. 2 times 90 is 180. So it like was somewhere down here. I know that's hard to figure out, but that's what's at. What's 2 times 100 degrees? 100 degrees. I know we didn't do degrees, but 100 degrees is like right up there. What's 2 times 100? 200 is like right here somewhere. That's in quadrant 3. So it's right at 135 degrees where it changes, doubling it. 135 doubled is 270. All right, so that I do want to actually make you think about that a little bit. All right, and then understand a little bit higher level. All right, and then I don't think I have to do both of these, so we'll do this one. This is again sine alpha, cosine beta. What's the sign? Positive or negative? What's the sign? Positive or negative? Negative, and then you switch them. Sine beta, cosine alpha. And then I'm not going to zoom in yet. I'm doing my replacements now. What sine of alpha? I have to go to this one, root 5 over 3. What's cosine of beta? I have to go to this one, which is 3/4. So again, this is not unit circle evaluations. These are different ratios. Then I have to go to B again and take the sine of B, which I already did. And then I have to go to cosine of alpha over here and put negative 2/3. Okay, you can see your ratios if you took the notes there. Now I can zoom in really large. All right, this one is 3 root 5. I'm not doing the other one. It's the same idea. 4 times 3 is 12. What's a negative negative? What does this become? These cancel. I'm going to go ahead and do this. Those cancel within that product, and then this is 2 root 7 over 12. You don't have to, but we'll close this off by writing this one more alternative form. If this was multiple choice, this would probably be the one that's written. Probably. That's what I feel. I know our old test generator always did it with a common denominator. All right? Okay, I don't think this is a really bad day. I think it's pretty doable. So, got to do your homework now. Here he goes again.